Hi everyone, welcome to this supplementary video. So this supplementary video is about the evaporation problem that we have discussed in the class. And I just wanted to go over one another variation of the problem, just to show you how every conservation equation and boundary condition are consistent. So just to remind you that we discussed this problem in class where we have this liquid column of density Cl, which is pure B. So only B is present in this liquid, and it's evaporating out into the air. Air represented as A into the column, and there's a binary gaseous diffusion problem in the vapor phase, which is this gas phase here, and the liquid phase is pure B. So in the gas phase, we actually found that the two fluxes here, the fluxes are constant, and we found the value of the fluxes in terms of velocity of the interface VI. So this is the velocity of the interface VI. Okay, so I briefly mentioned this in the class, but I want to kind of emphasize this further of how to think about molar and mass average velocity. So the molar average velocity are simply in the gas phase are simply NAY plus NBY by C, NBY by C. And we have discussed that because C is constant in this problem, which is given to us, small c is constant, which is CA plus CB is equal to C is equal to constant. And because NA and NBY are also constant, molar velocity is constant. Okay. However, if I want to write the mass average velocity V, then I will say it is NAY MA plus NBY MB by rho. And we've discussed because rho is not necessarily constant, remember that rho is equal to MACA plus MBCB. And because CA plus CB is equal to constant, it will be rho A is equal to C minus CB plus MBCB. And CB is changing from 0 to CB naught. So, because CB is changing, rho is also changing. So velocity is not necessarily constant, but we can still find the value. If we substitute the value for a given location, we can find the value. So let's say velocity would be then NAY is minus CL minus CB naught MA plus NBY, which is C minus CB naught. Sorry, I think I might have done the opposite. So NAY is first, so C minus CB naught, which is C minus CB naught times MA times VI plus NBY, which is minus CL minus CB naught minus CL minus CB naught into MB into VI by rho. Okay, so this is just the velocity. So all I have done is I've substituted the value of NBY here, NBY here, and I've said this is my velocity. Okay, so one way to think about this, and now I'll be a little bit more kind of at a location. So this is velocity at any general location. Okay, so now this is velocity at any general location. But what is V at y equal to h of t? Okay, so how will I find V is equal to y equal to h of t? So note that C, CB naught, VI, the numerator is constant. All I really need to do is to take the denominator, which is small rho, and I will substitute the density at y equal to h of t, and I will get that value as well. Okay, so that is one way to think about it. Another way to write this velocity V is this. So at y equal to h of t, again, I'm only thinking of y equal to h of t. C minus CB naught is my concentration of A, right? So this is C minus CB naught is concentration at this particular location, right? This is CB naught. So CA is C minus CB naught. We have discussed this in the class. CA is equal to C minus CB naught because CA plus CB is equal to small c. So CA MA is actually rho A VI, okay? Rho A VI minus CL times MB is rho L. So this is minus rho L VI plus CB naught MB, and CB naught is again the concentration at y equal to h of t for rho. So this is rho B VI by rho, or another way to think of this is minus rho L plus rho A plus rho B whole VI by rho. And I'll just finally give you the result. And this actually becomes, oh, my mistake. This is just to clarify this. I meant minus rho L plus rho A plus rho B VI. And you can verify this if there's any confusion. This becomes essentially minus rho L minus rho VI by rho. Okay. So this is finally, basically all I have done essentially is just simply find the mass average velocity given the molar fluxes of AY, BY, and AY and BY. And at y equal to h of t, I just rearranged and written this in a little bit more compact form. Okay, so it's not looking like a long expression. And why did I do that? So this is the velocity I find, when I really do the full problem, do an interfacial balance on each species, I sum them up. Now, the other approach, which again, it's not common, I'm just showing this for you for kind of you can appreciate how everything comes together, is we can also use continuity equation. So if you want to use continuity equation, okay, then I remember that continuity equation is del rho by del t plus del dot rho v is equal to 0. Okay, and this is our system. I again want to remind everyone that this equation is always applied at each phase. This is not like this cannot go across the interface. This is at each phase, and then we will do an interfacial balance. Okay. So this is a pseudo-steady system, so we can knock this term out, and then we'll simply get d by dy of rho vy equal to 0. So true in each phase. So remember, true in each phase. Don't forget it's true in each phase. Okay. Now, all this tells me is that rho vy is constant. So this means rho vy is constant. Or just let's just say rho v, because we're not using, it's implied it's a 1D problem. Let's just say rho v. It is implied it's in the y direction. Okay? Rho v is constant. Now there are two times. Again, one time is in the gas phase, I will say rho v is constant, and similarly I'll say rho lv in the liquid phase. This is the gas phase equation. This is the liquid phase equation. It's constant. Okay. The rho LV is constant. Now, another way we know that in the liquid phase, density is not changing. It's pure liquid, so density is not changing. And we know that the velocity cannot occur at this bottom container. There cannot be any velocity. It cannot have any liquid, going on normal to the surface. So this velocity will be 0, and rho L is constant. So that means this whole term is actually equal to 0. So this means V is equal to 0 in the liquid phase. Okay. And rho V is equal to constant. Again, the rho is changing, so my V might be changing, but the multiplication of the two would always come out to be constant. So that is the other thing we have. All right. So if we have that, if we kind of if we get this result, then let's try to now apply the interfacial balance on continuity equation. Interfacial balance. Okay. The interfacial balance is F minus BVI in the first phase divided with N minus F minus BVI second phase divided with N plus B is equal to 0. And remember that phase 1 and phase 2, we always take the normal going from phase 1 to phase 2. Okay, that's the convention for going from phase 1 to phase 2. Okay, so it's just a y direction. This is case equal to EY. So now, here my B is rho V, my B is rho, and my flux is rho V. Remember that there is no diffusive flux for total mass. We have discussed this. Diffusive flux is defined only for a species. When you think of the total system, there is no diffusive flux. So if that is the case, then what I really get here is, and this is at the interface, so y equal to h of t. In the gas phase, my flux is rho v. Okay, rho v. This is the velocity at y equal to h of t. Okay, minus rho vi at again y equal to h of t. Then minus. Now I will do rho L in the second phase. It's the liquid phase. So this is the liquid phase, right? So the rho L into V, velocity is 0 in the liquid phase, as we have discussed now. So that goes away. But I will have some velocity of the interface. So I'll get plus rho L Vi and there is no BS, so we get this equal to 0. Okay. So why am I doing this is because if you rearrange this, you get V is equal to Y of H of T is equal to rho L minus rho L minus rho VI by rho. And this is the same as the equation I had derived here. Okay. So there's the same equation using the quantity equation, or you can use the species balance. So the whole point of showing this is that it has to be consistent. All of these transport equations it cannot be that quantity equation will somehow not work. However, we obviously use the most convenient form, and because we are really interested in just the species concentration A and B, we don't really have to use quantity. But if you use quantity, you can still get the right answer. And this really came out of the discussion from a student who had asked me this question last year. So I figured I'd create a supplementary video and clarify this. Okay. So hope this video was useful, and let me know if you have any questions, and I look forward to seeing you in the lecture.